Namaste, welcome to the class. So already we have discussed about how the nucleus is formed, what are the components of nucleus, and we called it as nucleons. All the people who are living inside the nucleus are nucleons, and their protons and neutrons, how they are characterized by two numbers, atomic number and mass number, right? So every element is represented by two numbers, Z and A. Z is atomic number, A is mass number. A minus Z gives the number of neutrons, and positive charge of the nucleus is because of the protons inside the nucleus, and mass of the nucleus is because of the mass of protons as well as neutrons. Protons and neutrons are very heavy, that is why nucleus is very heavy. Electrons are very lighter, that's why most of the space in the atom is empty, because electrons are revolving outside the nucleus, and nucleus is dense and it is very tightly held, and it is the center of the atom. Okay, and we studied about nuclear the size of the nucleus is, and the shape of the nucleus is almost spherical in shape, and the volume of the nucleus should be directly proportional to mass number, because more the number of protons and neutrons, that is nucleons, more will be the size of the nucleus, and of course it will be in the order of Fermi itself. And now suppose volume of the nucleus is directly proportional to mass number. You know that volume of a nucleus of radius r is 4 by 3 pi r cube is proportional to A, but 4 by 3 pi is a constant, so r cube must be proportional to mass number, or r is proportional to cube root of mass number. R is equal to r naught, which is a constant, a to the power 1 by 3. So this is the equation which gives you the radius of a nucleus, which is almost spherical in shape. And all the nucleons are bound inside the nucleus with a very strong force called nuclear force. And always, for any force to exchange between two particles, whenever there is a force between two particles, some particles must be exchanged between the two in order to have a force. In order to have such a strong force between neutron and proton, and proton and proton, and neutron and neutron. And you know that nuclear force is charge independent. It doesn't depend whether the two particles are charged or whether they are neutral, and one is neutral, another is charged. Proton, neutron, 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 proton, proton. Every nucleon attracts every other nucleon with the equal nuclear force. It is charge independent. And when they attract, they want some particles to be exchanged, and those particles are called mesons. Right? That is not in the syllabus exactly, but better you know it. Mesons are the particles which are exchanged between two nucleons when there is a nuclear force between them. And nuclear force is the strongest force, and it is only a saturated force, because a single nucleon can attract only a fixed number of nucleons around. It doesn't attract every nucleon inside, and it is a short range force. Nuclear force can exist only within a Fermi range, that is within the nucleus, and outside the nucleus it suddenly vanishes beyond some 1 Fermi or so. Its value will be very less. So it is not a long range force like gravitational force, but within that Fermi range, 10 to the power minus 15, within that distance, it is very strong. And if the distance is very, very less, again it becomes repulsive. So yesterday in the previous class we were discussing about that nuclear force at the core of the nucleus, it is repulsive, but within a Fermi range it is 10 to the power minus 15 meter range, it is attractive, and outside 1 Fermi it is 0. So if you draw a graph of potential energy between two nucleons, whether it is two protons, whether it is two neutrons, so neutral neutrons, or a proton and a neutron, whatever it is, right? You fix them at a certain distance and try to find out the potential energy. And potential energy for an attractive force is taken negative, you know it. Potential energy of a repulsive force is taken positive. So whenever there is a bound energy, it is taken negative. So electron has a negative potential energy, right? Because it is bound to the nucleus. There is an attractive force from the nucleus which acts like a centripetal force. Now here, the two nucleons, when they are held separated by a certain distance, what type of nuclear force will exist between them? That is what you have to think of. If they are very close, and if they are far away, if they are at a medium distance, and if they are too much close, how will be the nuclear force? And now I will write the energy, potential energy when they are held separated and far away and very close like that. I will write the energy in the million electron volt range. So energy, potential energy in million electron volt. I want negative energy also, because you know that potential energy is negative when there is an attractive force between two nucleons. The electrostatic potential energy between two protons will be positive, but it is very less, because electrostatic force is very less stronger than nuclear force. Okay, now when I have to write here, say 1 Fermi. So this is Fermi range. 1 Fermi means 1 into 10 to the power minus 15 meters. So distance between the two nucleons in Fermi is 10 to the power minus 15 meters. 1 unit is 10 to the power minus 15 meters. And this is 2 and this is 3. If it is like this, and suppose this is minus 100 million electron volt, this is plus 100 million electron volt. Potential energy is in million electron volt. Then you will find that the nuclear force is and it will drop to 0 if you go beyond 1 Fermi, right? Beyond 1 Fermi, that means outside the nucleus, nuclear force is 0. So it is not a long range force, it is a very short range force. So here beyond certain range it decreases to 0. So it will be somewhere here. And within 1 Fermi, the nuclear force is strongest within the nucleus. So in the range of the nucleus, within the nucleus, the two nucleons can attract each other with their strongest force called nuclear force, and it will give high potential energy but negative. So it gives a high potential energy here and becomes very maximum at very close to 1 Fermi. And if you come beyond below 0.8 Fermi, that is much less than 1 Fermi, what happens is the nucleons are very close. That is what we were discussing in the previous class. At the center, suppose the nucleons come together by attracting themselves with nuclear force. When they are too close, the nuclear force becomes repulsive, because even if the distance is very close, and even then the nucleons keep on attracting, what happens is the whole nucleus will collapse. It will collapse into a very small entity and with production of large amount of energy. So the nucleus will not be stable. So in order to avoid this, the nature itself has done a repulsive core. How? And once the distance between the nucleons, because of attraction of nuclear force, goes below 0.8 Fermi, the nuclear force becomes repulsive. So the energy suddenly increases and it becomes positive, because once they become repulsive below the distance of 0.8 Fermi, once the nuclear force is repulsive, now you have positive potential energy, because it is a repulsive force. So the energy goes like this. So you might have seen that graph in the notes. So see that graph in the notes. It says that beyond 1 Fermi, the potential energy decreases to 0, and it is negligibly small, right? It decreases to 0, and at around 1 Fermi, it is highest but negative. But within 0.8 Fermi, it becomes positive and it becomes repulsive. So nucleus is always stable; it doesn't collapse. Okay, nuclear force is the strongest force in the nature, and when you write the properties, it is attractive in the Fermi range, and 10 to the power minus 15 meter, but it is a saturated force. One nucleon can attract only few nucleons around it, and it is a short range force, because it cannot exist outside the nucleus, and it is a charge independent force. It doesn't obey inverse square law. It is uniform throughout the nucleus, right? Okay, and then what did we see about the nucleus and charge of the nucleus? Charge of the nucleus is number of protons into charge of each proton. Now when you write the mass of the nucleus, that is what we have to see next. Mass of the nucleus. Mass of the nucleus is the mass of the constituent protons and neutrons inside the nucleus, right? And we are concentrating only on the nucleus now. Mass of the constituent protons and neutrons is called mass of the nucleus. Now what are the elements present inside the nucleus? Neutrons and protons. And the mass of a proton and neutron are almost same, except in a few ranges of say third to fourth number after decimal point. It is different. Up to that it is almost same. So but I will take mass of proton as mp, mass of neutron as mn. Then mass of the nucleus is Z into mass of proton plus A minus Z into mass of neutron, correct? Because number of neutrons is A minus Z. We don't have a separate number indicating the number of neutrons. A minus Z represents the mass of neutrons. Now this should have been the mass of the nucleus. But when you calculate the mass of the nucleus, you will be surprised to see that mass of the nucleus is not the mass of the proton into number of protons, and number of neutrons into mass of neutron. You won't get it so much. You will get lesser mass. Why? Does it mean that there are the number of protons and neutrons inside the nucleus are different? No. The number of neutrons and protons, what we take it from these examples. I will take an example. For example, in oxygen, atomic number 8, mass number 16. Then the number of protons, 8. Number of neutrons, 16 minus 8, 8, right? So it is 16 minus 8. So you calculate the mass of 8 protons and 8 neutrons, 16 minus 8 neutrons. You will get a value. But surprisingly, if you take that oxygen nucleus and weigh it, it will be weighing lesser. So does it mean that there are no 8 protons and 8 neutrons inside? There are 8 protons and 8 neutrons. Then what is the problem of calculating the 8 protons, 8 neutrons mass, and that is not equal to the mass of the nucleus of oxygen? So either the number of protons, neutrons, what you have assumed is wrong, or the mass of neutrons and protons must have changed. No. The total mass has been reduced because some amount of mass has been lost to form the nucleus itself. There is an energy needed. Suppose you want to form the nucleus of oxygen. What are the things you will purchase? Simply we will imagine it like that. I want to form an oxygen nucleus, sorry. If you want to form oxygen nucleus, you have to purchase 8 protons and 8 neutrons from somewhere, and place those 8 protons and 8 neutrons together and then form the nucleus. And who will do this job first? Even if you bring 8 protons and 8 neutrons, is it over? No. If you purchase groceries, all the items needed to prepare some delicious food, say for example some Mysore pak, then is it over? No, you have to prepare it. Somebody should put energy and they have to prepare it, and some energy is needed to prepare it, and energy is needed to prepare an oxygen nucleus starting from 8 atoms, 8 protons and 8 neutrons. So that energy will not be obtained from somewhere else. That energy will be obtained by losing some amount of mass while forming the nucleus itself. That is why total mass of nucleons after forming the nucleus will be less, before forming the nucleus will be more. And that is why mass of the nucleus will not be this one. Okay, mass of the nucleus is not this one. Mass of the nucleus is different. I will take it as m. This is the actual mass of the nucleus. This is what do we expect the mass. Taking individual protons and neutrons into consideration, this is what the mass we expect, and this is the mass of the nucleus, say. Then we get a difference, right? Theoretically calculating the exact number of protons and neutrons and finding the mass, and finding the actual mass of the nucleus separately will give you a difference. Actual mass of the nucleus is less, and mass of the individual protons and neutrons when added together will be more. So actual mass of the nucleus, if you take this m, then we define a term called mass defect, right? I'll change this as mass defect. What do you mean by defect? Defect means difference here, right? The actual mass of the nucleus is found to be lesser than the mass of individual protons and neutrons that are expected to be inside. That difference is called mass defect. So how do you write the mass defect as? Z into mass of protons plus A minus Z into mass of neutrons. That should be the expected mass. That is not the mass actually, practically, if you find the mass of the nucleus. Minus actual mass of the nucleus. That is mass defect. Mass of the nucleus is this much, which is lesser, and mass of individual protons and neutrons when added together we get this one, right? So take the difference. That difference is called mass defect. So mass defect is defined as the difference in the masses of actual nucleus and the individual protons and neutrons inside. The total mass of individual protons and neutrons, what we expected, and the actual mass of the nucleus, that difference is called mass defect. This mass difference has occurred because some amount of mass has been directly converted into energy to form the nucleus. Now where is it now? That is in the form of binding energy of the nucleus, and that is used to form the nucleus, and that is given as the energy to the nucleus. If you take a soap bubble, if you take a water drop, you know that it has a binding energy. And soap bubble, if it has to remain spherical in shape, there is a surface energy on the molecules. The molecules of the surface will have an extra energy, that is called surface energy, and that is called surface tension, surface energy per unit area. So it should have an energy outside, otherwise it cannot form such a spherical shape. And if you want to pack sugar in a plastic packet, then the plastic packet should have an extra energy, otherwise the sugar will come out, right? Similarly here, that nucleus as a whole will have some energy. Now how to find out how much is the energy of the nucleus? What is the energy of helium nucleus? What is the energy of oxygen nucleus? What is the energy of iron nucleus? And which is highly energetic, which is stronger? We want to define it all. And that binding energy, we call it as binding energy. So define binding energy. Binding energy is the energy required to form a nucleus starting from individual protons and neutrons. Or binding energy is the energy obtained from the mass defect. Because you will lose this much of mass, right? I'll call it as delta M. Okay? I'll call this as delta M. Delta M is the mass defect. And that much of mass is lost. Convert it into energy. You know that Einstein's mass energy relation. Any mass or mass can be converted into energy. Any energy obtained from losing m amount of mass is given by, according to Einstein's mass energy relation, E is equal to mc square. You know this. E is equal to mc square is the energy obtained by losing some mass m or destroying some mass m. So if you lose this much amount of mass defect, that is mass of the individual protons and neutrons minus actual mass of the nucleus, that is mass defect. Convert this into energy. So what is binding energy then? Binding energy of any nucleus is given by delta mc square, where delta m is the mass defect. Because you have lost this much of mass, so you convert it into energy, you will get the binding energy of the nucleus. So that much amount of mass is lost, not only just to form the nucleus, just to construct the nucleus, to give energy to the nucleus, and it is now stronger now. It is stable and it is very strong, and that strength is given by this binding energy. Okay, it is the so how can you define then mass defect? Mass defect is the difference in the masses of individual protons and neutrons and mass of the nucleus. What do you mean by binding energy? It is the energy required to form a nucleus starting from individual protons and neutrons. Starting from individual protons and neutrons, how much energy is required? Or binding energy is the energy equivalent of mass defect. How much energy you will get if you lose mass defect amount of mass? That is called binding energy. Now, when you calculate binding energy of nucleus, it will not be in the order of joules and so much of amount of joules or so. And if it is in the form of in electron volt, right? In the range of electron volt, sorry. And that means in the 10 to the power minus 19 joules range. So better you convert it into joules. Electron volts. We put it in that range. Now, even mass, how much mass is lost while forming a single nucleus? Very, very less amount of mass. In the order of 10 to the power minus 27 kg. Because you know the mass of protons and neutrons. So when you mass of a proton or neutron itself is 1.66 and some digits, different digits, into 10 to the power minus 27 kg. So when you form a nucleus, you are losing a small amount of mass. That itself will be in the order of 10 to the power minus 27 kg. So when you have so much of mass, let us have a new unit to measure that mass and to measure that energy. Of course, the measuring energy is done in electron volt, right? The energy obtained by accelerating one electron in a potential difference of 1 volt. You know that 1 electron volt is 1.6 into 10 to the power minus 19 joules. That all the things we have studied. Now, the thing is, yes, how to measure that mass. And you know that mass spectrograph is a instrument which using which we can measure the atomic masses, and it is also useful to find out isotopes and all. Now, we have to find out the binding energy and a separate unit for binding energy and mass defect. Yes, that is called atomic mass unit. What is atomic mass unit? We represent it by a symbol U. What is atomic mass unit? So in order to define atomic mass units, you see, whenever you define a unit for measuring mass or anything, we have a standard, right? For example, what is 1 kg? It is the mass of that stone that we get in the shop, right? All the shops weigh the same as 1 kg. The 1 kg of one shop, 1 kg of another shop, they are exactly equal. They must be exactly equal. Otherwise, you will better you rush to a shop where 1 kg stone is much heavier. You will get much grocery and whatever you purchase. They are equal in mass. Even the 1 meter length scale is equal in length in all the shops. So that is taken as standard, and there is a standard mass. There is a standard stone for 1 kg mass. Similarly, what is one atomic mass unit? In order to define it, we take carbon as the atom. You take carbon atom and measure the mass of one atom of carbon and take it as one atomic mass unit. One atom of carbon and divide it by 12. Then that is taken as one atomic mass unit. It is 1 by 12th of, so you have to divide it by 12. One atom of carbon. 1 by 12th of one atom of carbon, 1 by 12th of the mass of one atom of carbon, that is called one atomic mass unit. So one atomic mass unit is 1 by 12th of the mass of one atom of carbon 12. 12 is its mass number. So 1 by 12th of the mass of one atom of carbon 12, that is called one atomic mass unit. Right, because why do you divide it by 1 to 12, sir? Simple, there are 12 people inside the nucleus of carbon. 6 protons and 6 neutrons. You know 6 carbon 12, you write it like this, right? Configuration, 6 carbon 12. 6 protons, 12 minus 6 neutrons. So try to distribute it to all the nucleons, then it is one atomic mass unit. So 1 by 12th of the mass of one atom of carbon 12, that is called one atomic mass unit. And you might have studied this in chemistry, right? And in chemistry you usually define 1 mole, Avogadro number of molecules. And we select carbon because carbon is an atom which weighs exactly the mass number, 12 gram. 1 mole of carbon weighs exactly 12 gram. 1 mole of carbon means how much? It is 6.02 into 10 to the power 23 atoms of carbon. You know, you want to find out 1 by 12th of one atom of carbon 12, right? You want to find out the mass of one atom of carbon 12 atom and divide it by 12, correct? So if you, first of all you get what is the mass of one carbon 12 atom, then divide it by 12. So what is the mass of one carbon 12 atom? We know 12 gram, but 12 gram is not the mass of one carbon 12 atom. It is the mass of 6.02 in 10 to the power 23 atoms, that is Avogadro number of atoms. So what is the mass of one atom? Divide it. So one atom of carbon 12, mass of one atom of carbon 12. If you want to know it, it is equal to 12 gram is the mass of, okay, I will convert it into kg. 12 gram is the mass of 1 mole of the carbon atoms, that is 6.02 in 10 to the power 23. So 6.02 in 10 to the power 23 atoms weigh 12 gram. Then what is the mass of one atom? Divided by 6.02 into 10 to the power 23 atoms. That is the mass of one carbon 12 atom. But what is the atomic mass unit? It is 1 by 12th of the mass of one atom of carbon 12. 1 by 12. Divide it to 12 because this gives the mass of one atom. But one atom contains 12 people inside, 6 neutrons, 6 protons. Share them. Share the mass to them. 1 by 12th of 12 gram for 1 mole. So each atom is, so there are this many number of atoms. So one atomic mass unit, so that is a separate unit we try to use, because you see there are some convenient units. You can't rely on SI system always. Suppose you want to measure the mass of sand in a lorry, you can't put it in milligrams or grams or kgs, right? You put it in quintals. Suppose a doctor says the mass of a newly born baby, it is not put in quintals, it is put in pounds. pound. They say the newly born baby should be of so much pound, and this is so much pound, and this is a healthy baby and all. So everywhere we have a convenient unit, we can use it, but there is a standard unit called SI system. But we can't depend on the SI system always. So that is why we depend on atomic mass unit here, because if you want to try to put it in kgs, it will be 10 to the power minus 27, 20 to the power minus 30, something like that. So we will have a convenient unit. So one atomic mass unit is 1/12 of 1 atom of carbon-12 mass. 1 atom of carbon-12 weighs 12 gram by Avogadro number, because Avogadro number of atoms weigh this much. So what is this answer? This is equal to, and if you calculate this, 1 by 6.02, right? So 12 will cancel, and this will be minus 26, and 1 by 6.02, that will be 1.66. Later digits I don't write, it is 0.166, and I'll rub this now because it is unwanted, it's already substituted. 0.166 into 10 to the power minus 26 kg, because I have already converted it into kg. So this atomic mass unit is 1.667, you can write, into 10 to the power minus 27, because I have to multiply by 10 and divide by 10. Divided by 10, multiplied by 10 will make it 1.66. Divided by 10 will make it 10 to the power minus 27 kg. This is atomic mass unit, right? So this is the convenient unit. So we express it in 1 atomic mass unit, 2 atomic mass unit, 1U, 2U, 10U and all. So when a nuclear fission occurs, so many U's of mass is lost and it is converted into energy. So that becomes very easy. Okay, now where we are now? Yes. So this is an important part, either for 1 mark or to calculate. Obtain the mass, express 1 atomic mass unit in kgs and explain it. It is the 1 by, or define it and explain it. 1/12 of the mass of 1 carbon-12 atom. Okay, now if you know this, suppose I express the mass in atomic mass unit, how to convert it into energy? Now we will come back to binding energy. Binding energy of a nucleus is the energy required to form the nucleus, or even the energy required to break the nucleus. It is one and the same. So energy required to form the nucleus from individual protons and neutrons, or energy required to break a nucleus to form the individual protons and neutrons, both are binding energies, or it is equal to the energy equivalent of mass defect. So what is mass defect? Mass defect is the difference in the masses of mass of the actual nucleus and mass of the individual protons and neutrons. Z into mass of proton plus A minus Z into mass of each neutron minus mass of the nucleus. That is mass defect. If mass defect is given in kg, directly convert it into binding energy in the form of E equal to mc square. So the binding energy is I'll write binding energy is equal to delta m into c square, provided delta m is in kg, gram and milligram and all, right? Suppose you are given when a nucleus is formed, the mass defect was found to be, what do you mean by mass defect? Mass defect, as we started with individual and protons and neutrons, when weighed it, and after forming the nucleus there is a difference, and that difference is mass defect, and it is found to be, say, something like 3 into 10 to the power minus 27 kg. Mass defect was found to be 3 into 10 to the power minus 27 kg. What is the amount of energy? What amount of energy is binding energy in the nucleus? In the form of binding energy in the nucleus, what you can do is that is equal to 3 into 10 to the power minus 27 kg is the mass that has been lost in the form of energy, converted into energy. C square, velocity of light, 3 into 10 to the power 8 whole square. So binding energy is equal to, so you can multiply this will be 9, because 9 into 10 to the power 16 after squaring. This is 27 into 10 to the power minus 27 plus 16 minus 11, correct? Yeah, 9 into 10 to the power 16 minus 11. This much of joules. So if you want to express the energy in joules, and if the mass is given directly in kgs or grams, put E equal to mc square, provided m is in kg. Convert it into kg. But if m is given, delta m, that is mass defect, if it is given in atomic mass unit u, how to find out the binding energy? One thing you can do is, one atomic mass unit is 1.66 into 10 to the power minus 27 kg. So convert that atomic mass unit into kg and use E equal to mc square. That is also possible, right? So one method is convert one atomic mass unit as 1.66 into 10 to the power minus 27 kg. For example, if it is given 5 atomic mass unit of energy is lost, convert it into kg, directly equal to mc square. On the other hand, you can have a direct connection between energy and mass defect in atomic mass unit. How it is so? Or how is it expressed? Let us find out. Suppose 1 kg of mass is lost. How much energy is obtained? E equal to mc square. M 1 kg. C square. 9 into 10 to the power 16. That is 3 into 10 to the power 8 whole square. 9 into 10 to the power 16 into 1 kg. That much of amount of joules of energy is lost. Energy is obtained or lost. Now, from 1 kg of mass, if it is in AMU, what you can do? What is the energy equivalent of? What is the energy equivalent of 1 nu? That is what you have to do. Because usually in nuclear physics, when you go to the nuclear level, we express the masses in atomic mass unit. That is a convenient unit. You need not have any 10 to the power of minus something like that there. You can express it in direct atomic mass unit. So if you lose 1 atomic mass unit of mass, what is the energy that you obtain? Express in electron volt. Now what you can do is, you know that 1 atomic mass unit is 1.66 into 10 to the power minus 27 kg. It is 1/12 of the mass of 1 atom of carbon 12. If it is so, the energy obtained by 1 atomic mass unit is mass into c square. 1 atomic mass unit is nothing but this much of kg. So 1.66 into 10 to the power minus 27 kg into 3 into 10 to the power 8 whole square. Now if you calculate this, what will you get? You will get the answer in joules. Am I right? That is the answer in joules. I want to express it in electron volt. So the question is like this now. Express the energy obtained by destroying 1 atomic mass unit and express it in electron volt. Express the energy obtained by destroying 1 atomic mass unit of mass in electron volt. So you have substituted mass in kg, you have substituted c square. This is in joules. What is energy in electron volt? That is equal to 1.66 into 10 to the power minus 27, 9 into 10 to the power 16 divided by, okay, that is, you know how to convert energy in joules to energy in electron volt. 1.602 into 10 to the power minus 19 and so many electron volt. So what is the energy equivalent of 1 atomic mass unit? See the words here, energy equivalent of 1 atomic mass unit, right? It is energy equivalent means 1 atomic mass unit is not equal to so many million electron volt. By destroying 1 atomic mass unit of mass, when you lose so much amount of mass, how much energy we will get, right? Remember, mass itself is not energy. You can convert convert mass to energy. That is what Einstein says. It is Einstein's relation. And another thing we can have, vice versa is also true. You can convert energy to mass. Just think of light energy, right? Photons. You can convert it into mass. Of course, that is possible in nature. It is happening, but it's not happening in a large scale. If all the light coming from the sun is getting converted into mass, then we won't have any space here, right? So it is not possible. Only that at some parts it is done. So, but it is possible. Energy also, so Einstein says energy can be converted into mass and mass can also be converted into energy. You can get it into from the equation E is equal to mc square. It is vice versa also, it is true. Okay, energy is equal to, we have divided it by so much, so many electron volt we should get 1.66 into 9 and divided by 1.602. You can verify it. So that gives to I have left with some numbers here. You can check it. 1.67 actually, this one 1.67, 66 and some digits you have, 67 into, and this is not exactly 3, this is 2.997 something, right? Exact velocity of light in that air or vacuum, and 2.997, that you have to substitute, and after substituting these values you will get it like this. Yes, 931.5 into 10 to the power 6 electron volt, that is equal to 931.5 million electron volts. This is the energy that you obtain, right? So energy equivalent of one atomic mass unit is 931.5 million electron volt. This formula, or this relation, not a formula, it is exactly not a formula. This relation helps us to find out the energy equivalent of any mass defect. Any mass defect given in the form of atomic mass unit. Sir, some 10 atomic mass unit of mass is lost in a nuclear reaction, say. When the reaction started, finally when we got the products were having a mass which is lesser by 10 atomic mass unit. How much energy must have been given? Don't use E is equal to mc square, because mass is in atomic mass unit. We know that one atomic mass unit one atomic mass unit of mass, if it is destroyed, we get this much of an amount of energy, 931.5 million electron volt. If 10 atomic mass unit of mass is lost, how much energy we will get? Simple cross multiplication, 9,315 million electron volt, finish. So one atomic mass unit is equivalent to, it is not equal to, if you destroy it, whatever the energy we get, so it is equivalent to 931.5 million electron volt of energy. When you work out problems, it will be very clear to you, right? So don't write one atomic mass unit equal to 931.5 million electron volt. They are not equal. One is energy, another is mass. But if you destroy this mass, you will get that much amount of energy. So this is the energy of the nucleus. So nucleus has got an energy within it, and that is called binding energy of the nucleus. And binding energy is the best example for Einstein's mass energy relation, that mass can be converted into energy. So suppose you are asked to write an example. Give an example for Einstein's mass energy relation which says that mass can be converted into energy. Example is binding energy. How is binding energy obtained? How the nucleus is formed? Just by losing some mass. From where do you get mass? By losing the mass of constituents itself, right? So total mass of the nucleus will be lesser than the masses of individual protons and neutrons when we started forming the nucleus. So when we started with the 6 protons and 6 neutrons in order to form carbon, then finally what we obtain after forming the carbon nucleus will be lighter than 6 protons and 6 neutrons, and that lost mass is converted into energy. That is the binding energy of the nucleus. So if you want to break a nucleus, you must need that much amount of energy, and binding energy of the nucleus is very large. It is not so easy to break the nucleus. Suppose you break the nucleus, you get that energy. That is what the energy we get in nuclear bombs and fusion bombs, right? So that binding energy is obtained. So that Einstein's mass energy relation is equal to mc squared gave us answer to all these types of energies. Mass can be converted into energy. Okay. Now, sir, now we have studied about, so coming back to the nucleus now again. Nucleus has protons, neutrons, they are bounded by a nuclear force, so there is a binding energy to the nucleus, and it is spherical in shape. The nuclear force is strong, and we know the size of the nucleus is dependent on mass number A, and all the properties of nuclear force. Now coming to the binding energy. If a nucleus is having more and more energy, whether that nucleus is stronger? That is the first question. If a nucleus is having more binding energy, will it be stronger? And if a nucleus is having less binding energy, will it be weaker? We can't conclude. The total binding energy of the nucleus is not a measure of the strength of the nucleus. Whether the nucleus is very stable, very strong, and whether the nucleus is unstable, it is not very strong, at any moment it can break, right? If you just see in the beginning, Niels Bohr tried to explain the properties of nucleus in the form of liquid drop, right? When you take a liquid drop, up to some extent it was possible. When a liquid drop is taken and when it is vibrated, if it is a larger liquid drop, what happens is it breaks into two. And if it is a smaller liquid drop, it doesn't break because it is very stable. If it is too small liquid drop, it will combine with another drop and it will form a stable liquid drop. So when you have very small teams of people, if they are not strong in a town or in a place, they combine together to form a stronger team. And if the team is too large, then again there will be some conflict between the two people, and the team divides and becomes two stronger teams. In the same way, the binding energy, if you take the total binding energy of the nucleus, you can't conclude that whether the nucleus is stronger or not, whether it is stable or not. It may break or it may join to become stable. And all the answers are given because of another term, using another term called binding energy per nucleon. If a nucleus is stronger or weaker, we have to decide it not by binding energy per nucleon. How many people are there inside the nucleus? You have to share it to all the people. Then you have to decide whether the nucleus is stronger or not. What is binding energy per nucleon? Total binding energy of the nucleus divided by mass number. Why, sir, mass number? Because there are a number of nucleons inside the nucleus. There are a number of protons and neutrons inside the nucleus. Share it to all. Then see whether it is very strong or not. So binding energy by mass number, and there is one more name for this, specific binding energy. Okay, I'll write this full. Specific binding energy is binding energy per nucleon divided by mass number. What the nucleus which has got more binding energy per nucleon, that is stronger. Total binding energy may be more, but per nucleon when you divide it, which gets more binding energy, that is stronger. And the nucleus which has a less binding energy per nucleon, that is not much stronger. That is a weaker nucleus. It is very simple. And if you are more confused with this one, sir, why? If the binding energy is stronger in a nucleus, it should, is more in a nucleus, it should be stronger, na, sir. And if the binding energy less, it is less stronger, and it should be unstable nucleus. No. I will give a best example for it. For example, person A, his income per month is say 1 lakh rupees per annum. Income of person A is 1 lakh rupee per annum. Income of person B is 30,000 rupees per annum. Now, with this much of data, can you conclude that person A is richer and person B is poor compared to person A? No. Okay, this is per annum, it should be per month, right? Per month. Otherwise, okay, let it be, whatever it is, right? The income of person A is 1 lakh per month and this person is 30,000 per month. Immediately we can't come to the conclusion that person A is richer and person B is poor. You should have one more important data, that is, how many people are there in the person house of this person, how many people are there in the house of person B. Let us imagine that this person A is having 10 people in his house. That's why I have divided it by mass number, right? How many people are enjoying this total binding energy? That is very important. If more people are enjoying, that person will be poor. Suppose this person has got only say two persons, he and his wife, right? And here there are 10 people, he, his wife, children, grandchildren and all. So all are in a single house, right? All are depending on the person A only. Now what is the amount of money each person will get here? He has to spend 1 lakh rupee to the 10 people, and each person will get 10,000 rupees. Rupees per person. So you have to spend 10,000 rupees per person. What about here? 30,000 rupees is enjoyed by only 2 people. So everyone will get 15,000 rupees. So he is stronger, weaker. Correct? So it is not the binding energy which tells you whether the nucleus is stronger or not. It is the binding energy per nucleon which gives you whether the binding energy is, whether the nucleus is stronger or not. So you have to divide it by the total number of people who want to share it or who want to get the share. So then if it is more, if the binding energy per nucleon is more, then the nucleus is very strong, and if the binding energy per nucleon is less, then the nucleus is weak. So that's how it goes, right? So now a study was made for all the elements, on all the elements, about this specific binding energy or binding energy per nucleon. Binding energy per nucleon of carbon is taken, hydrogen is taken, helium, lithium, beryllium, nitrogen, oxygen, iron, calcium, uranium, every element is taken. You have all the elements in the periodic table, and binding energy of all these elements were studied, and they were put in a graph, but not the total binding energy. Once again I remind you, it is the binding energy per nucleon. When you answer this question, you must be very careful. I don't know whether this question will appear in the final exam or not. I will give you a clue that whatever the CBSE board has given, this small portion is deleted from it, but I do everything. You will study it now, at least to some extent. Then it is easy to leave later, but very difficult to add it once again. It takes a lot of time once the class starts if we want to add it once again. So we will study it now, because it is not very tough. All the things that you get in modern physics, that is atoms, nuclei, photoelectric effect, and again semiconductors and all, the things are very easy to follow, not very difficult. Okay, a graph is plotted with the binding energy per nucleon on y-axis, binding energy by mass number on y-axis, and mass number in x-axis. If you go wrong in writing any one of these, you will lose all the marks. Suppose it is involved in the syllabus. But this should be involved in the syllabus, because this is a very easy part, and those who find it difficult to pass in second VC, they will definitely write this graph and they will explain it, right? Okay, today I will show you the graph and explanation, and we will go to the next class. So binding energy, okay, where we are, a graph plotted with the binding energy per nucleon. That means in carbon there are 12 members. So total binding energy by 12 members. In nitrogen there are 14 members, 7 protons, 7 neutrons. So total binding energy by 14. Similarly different elements, right? So binding energy per nucleon by mass number, with mass number on the x-axis. If you plot a graph, it will be like this. A graph will be obtained like this, and the highest binding energy per nucleon was found to be here, right? It is almost of 8.75 million electron volt. Can you tell me which is the very strong nucleus and the stable atom, right? Very, very strong nucleus. It is iron, and it is found to be almost for iron, and here only in the neighborhood you will get calcium. Calcium is also very strong. You know, bones are made up of calcium, right? Iron, calcium will come in this range. So I will write iron, Fe, 56. And here you have some peaks, right? It looks like the tail of dinosaur, right? It is like this, or crocodile. Now, some elements have suddenly high binding energy, binding energy per nucleon, and the very neighboring element with just more mass number, suddenly it will have less, again more, again less, again more, again less. You will remember this curve if it is, pray God that these things will remain in the syllabus, so that you can score some marks in the theory exam. So here the elements are, this is helium, and this is carbon, and sorry, this is oxygen. This is lithium and nitrogen, oxygen. This is having a little bit more, because as you move forward, this curve comes forward and comes up, right? So that means this is oxygen 18 and this is oxygen 16. They are the isotopes of oxygen, right? Different mass number, same atomic number. And you know, carbon 12 and helium 4. Lithium comes next, lithium little forward, right? So coming to the top, moving forward and coming down. Less for lithium. For lithium, binding energy per nucleon is less than helium. Helium is stronger, lithium is not so much stronger. And here are only certain spikes. Lithium, hydrogen, helium, lithium, right? 6. Correct? Then nitrogen 14. Yes. And uranium and other elements will come here, right? Uranium 238, say 235 or 238. This is the binding energy per nucleon curve, and usually this is called binding energy curve. And if you observe the binding energy curve, you will find that elements having very, very less mass number, hydrogen, something like this, they are less stable, because binding energy per nucleon for them is very, very less. You just find out the elements which have less atomic number, less mass number, lesser than 10 or so, then they have less binding energy per nucleon. Elements having very high mass number, like uranium, they are also less stable, because they have their nucleus is very heavy and they have too many protons and neutrons. You will see the exact reason why they are not stable. Even though they have high binding energy, they have less specific binding energy. Binding energy per nucleon is very less. And elements which come under a mass number of some 130 to some 70 to 130, something like that. Exact number I don't remember. Elements having 30 to 170, and I will tell you it in the next class, the exact number. Elements having mass number from 30 to 170, 160 or 170, they have high specific binding energy. See, if you see this range, it is more than some 7.5 million electron volt. The highest specific binding energy, highest binding energy per nucleon lies at here, this one. That is 8.75 million electron volt. That is for iron. So I think it is 30 to 170, something like this. So elements having mass number in the range 30 to 170 are more stable, because their binding energy per nucleon is very high. And why it is so, we will see. And why these elements having less mass number have less binding energy per nucleon, and elements having high mass number also have less binding energy per nucleon. Only those which come under 30 to 170 range of mass number, they have a high specific binding energy, with iron standing with highest, that is 8.75 million electron volt. So this gives you clear idea that it is not the total binding energy of the nucleus which is required for calculating the strength of a nucleus. It is the binding energy per nucleon which is required to be seen in order to specify the stability of the nucleus. Binding energy per nucleon will decide the stability of the nucleus. So that is the curve, and we will analyze the curve again in the next class, so that I will get a chance of drawing it again, so that it will be an experience for me and I won't forget it in the next year, and experience for you also, because if you have a book in front of you and I draw it, even if you draw it along with me, then it will be the second experience. Otherwise I would have finished it now. So we will meet in the next class with a few more ideas of this, and we will have some problems also which are very interesting and very easy. So we will continue it in the next class. Thanks for watching my class. Keep watching the videos, don't waste the time, take care of your health, right? And we will meet in the next class. Thank you.